Okay, we're going to start chapter 14, and we're going to start it with the topic, which is all about functions. And so we're going to have a function f that goes either from the entire R2, which essentially you can think of the xy plane, so we're having a point in xy, and we're mapping it to the point f of xy. Or, more generally, we could have a function that's going from some domain D, which is a subset of R2, and that goes to some subset of R, or maybe all of R, where D is some subset of R2. Where this R2 you can think of essentially the xy plane. Okay, so here D essentially is your domain of your function f. And so in general you have the possibility that given a function, so for example here, if you're given a function f of xy is equal to x squared plus the ln of x plus y, then the domain of f, which is what we're denoting by D, that would be the set of all numbers xy, or the set of all ordered pairs xy, where x plus y is greater than 0, or the set of all xy, where x is greater than negative y. Of course, you can map that in the coordinate plane if you'd like to, but that's the general idea for domains. They're very similar to how you see it in one dimension. It's just now the domain sits in 2 dimensions. So for example, let's just graph this one. Let's graph the domain D. So let's start by setting y equal to negative x. That's a line. So here's the line. Let's do this now with a different color. The line y equals negative x. I guess I could have rewritten this probably in the more usual way, with this y is greater than negative x. It's the same thing. So essentially the domain then, if y is going to be greater than negative x, then we have to be sitting in this red region. So this red region, this is when y is greater than negative x, and that is the domain of D. So now once you have that, you can say, okay, we can consider the graph of a function. So the graph of f, what is that? That is the set of points x, y, f of x, y, where the ordered pair sits inside the domain D. Of course, if the domain is the whole plane, then it's the whole plane. So for example, do a couple of examples that essentially we've already seen, but they are just rewritten in functional notation. 2x minus 4y plus 1. And by the way, we can always think of these as, these are all functions in the form z is equal to f of xy. So when we say f of xy, we're essentially referring to the z value. Just like in one dimension, if you have f of x, you're essentially saying y equals f of x. So the analog is, if you have a function f of xy, it's z equals f of xy. So let's consider this function. We can ask the question for this: what is the domain of f? And for some of these, it's not hard to check. Some of them it is hard to check. You can also find the range of this function. What are the output values? In this case, what are the z values that pop out? And it's not hard to check that the domain here, if you have a polynomial function, the domain here is all of xy. So all xy, or simply all of R2. And the range here is all real numbers, is all real numbers. Okay, and this will be true because, well, what is this function actually? This is z is equal to 2x minus 4y plus 1, or 4y minus 2x plus z is equal to 1. This is a plane, and it's slanted, right? It's not a vertical plane. It's not a horizontal plane, because the normal vector here is 4, negative 2, 1, which is, you know, the orthogonal piece to that, which is this plane, is going to be slanted, and hence you can see that, you can kind of visualize that if you have a slanted plane, I'm not going to draw it, but you can, if you want to graph it in GeoGebra, you can. If you have a slanted plane, then the z values will go up to positive infinity at some location, and z will also go down to negative infinity as the plane sort of expands out further and further. So there, it turns out the domain and the range is sort of straightforward. Let's do an example which is just a bit more involved. So let's take the negative square root of 16 minus x squared minus y squared. So the first thing you want to do is sort of identify this surface. We have, in chapter 12, identified several surfaces. So let's write this as z is equal to negative square root of 16 minus x squared minus y squared. Now it's possible you can stare at that and immediately figure out what it is, but just in case it doesn't immediately strike you, one thing that maybe you can do is square both sides just to get into a form which is a little bit more recognizable. And so what you end up with is x squared plus y squared plus z squared is equal to 16. So this must be part of a sphere, because we know that this is the whole sphere. This is a whole sphere centered at 0, 0, 0, where the radius is 4. But remember, a full sphere is not a function. So this whole sphere is not a single function. It doesn't pass the vertical line test. There's sort of an analog of the vertical line test. Here's the xy plane, and if you keep drawing vertical lines that pass through, and it passes more than once through the graph, so if you have a sphere, for example, if you have this sphere, then these vertical lines, which maybe I should extend a little further, these vertical lines will cross the sphere twice. So this fails the vertical line test. Oops, not horizontal, but the vertical line test. So the whole sphere can't be a function. So this must be just part of the sphere, and indeed you can sort of see, since that z is the negative square root of 16 minus x squared minus y squared, this is actually the bottom half of the sphere. So we have the bottom half of a sphere with our coordinate plane sort of sitting right here. So what is the domain here? The domain is x squared plus y squared less than or equal to 16. The domain is kind of this green shaded piece right here in the xy plane. That's our domain. And our range, well, the smallest, so for our range, the lowermost point here, if you go to the bottom, we have the point 0, 0, minus 4. So the smallest z value is -4, and the highest z value is 0. So these are exactly the z values that are attained by this function, and hence you have this following range. So these are the kind of this is the kind of idea for these functions. By the way, you can also label what are called the level curves of functions, and those are curves when you take the function f of x, y, and you set it equal to some value c. So for example, in our particular bottom half of a sphere, say you set c to be like -1, right? Well, let's do a couple of them. Let's set z to be 0, c to be -1, c to be -2, and let's say c is equal to -4. All right, so these are what we're going to set f of x, y to be. So if we set f of x, y to be 0, then what happens? We have this equation, which essentially, when you square both sides and sort of settle everything down, you get x squared plus y squared is equal to 16. So this thing becomes this. So the level curve at c equals 0 is the curve x squared plus y squared equals 16. For c equals -1, you'll end up with x squared plus y squared equaling 15. If c equals -2, then you'll get x squared plus y squared is equal to 12. Again, remember you're squaring both sides, and then basically bringing over the x squared plus y squared to one side, the constants over to the other. And if you do c equals -4, you're going to get x squared plus y squared is equal to 0, which essentially is just a point, since that means that x equals 0 and y equals 0. So when you draw the level curves, let's draw those in red. So you have your xy plane here. You have a dot here at the center, right here, x equals 0, y equals 0. And this is at essentially z equals, right? Because these c values, these constants are actually, they're z values, right? Because we're setting f of xy to be those, which means z is equal to that value. So we can correspond this to z equaling -4. Oops, change color, let me put that in red. And then if you go to -2, you have a circle of radius to square root of 12, which is a little bigger than 3. I'm just going to approximate these. So you have a circle here. Oops, sorry. You have a circle here, and this is the circle that corresponds to c equaling -2, or z equaling -2. And then you have a slightly larger circle for z equals -1. And then at 0, you have the full circle of radius 4. Sorry, I ran out of space there. But this says z equals 0. So these are the level curves, which you can, again, just like we saw in chapter 12, you can sort of push these up and down to the respective planes, z equals -1, z equals -2, and they will be there. So let me just draw it one more time. So here's our coordinate plane. Here would be our z equals 0. We'd have a slightly smaller one here at z equals -1. A slightly smaller one again at z equals -2. And once we come down to to minus 4, here we'd have a single point. So you'd have your, doesn't look much like a sphere, it looks more like a paraboloid, but you get the idea. So these are the so-called level curves. Level curves. The level curves, of course, they're originally here, and then we move them down by their z location into the actual graph. So let's leave you guys here with a little exercise. So exercise. So let's say f of xy is the square root of x minus 4 squared plus y squared, and then plus 1 outside of the square root. So go ahead and find the domain, and go ahead and find the range, and go ahead and find the graph of f. Okay, we'll stop here. We will continue 14.1 in the next video.